Okay, this is a super quick, high-level explanation of my master's research, which involved knowledge compilation for defeasible reasoning, which was supervised by Tommy and Yese. So just to give a quick summary, my work tackles defeasible reasoning, which is where you reason with statements that are usually true rather than always true or false. Like a statement that says, if it's a bird, then it probably flies. This is a statement that is sometimes true, sometimes false, depends on the context. And that's called a conditional. And the way these are usually dealt with is by assigning them each a rank according to how general they are. And then when you get a new statement that you want to check its truth with regard to all the other statements, you disregard all the lower ranked statements until you get a collection of statements that are coherent, and then you perform inference based on those remaining statements. The problem is that this whole process is very computationally expensive. So what I do is I use the paradigm of knowledge compilation, where you basically spend a lot of computation to convert your information into a more computer-friendly representation. And then that allows you to perform new inference much more quickly later on. So this is all part of the field of symbolic artificial intelligence, which is basically where you represent knowledge through explicit rules and symbols, rather than just statistics and prediction like what you do with neural networks and machine learning. And this is a lot more closer to how humans reason. An example of this is just the basic Boolean formula that says if A and B are true, or this whole statement is true when A and B are true, or C and D are true. And these are just regular variables that can represent anything. And defeasible reasoning deals with conditional logic, where you have these statements that mean if A is true, then normally B is also true. So an example of this is the statement that says, if it's a bird, then it typically flies, but not always. And to give an example of this, say we have the collection of statements that say, if it's a bird, then it typically flies. If it's a bird, then it typically has wings. If it's a penguin, then it typically doesn't fly. And if it's a penguin, it's always a bird. This is ranked like this. So at the lower rank, you have the more general statements. The second lowest rank, you have the second most general statements, and then at the rank infinity, you have all the statements that always hold, no matter what, so they aren't defeasible. And if we got a new statement, and if we wanted to see if it was true or not according to this ranking, so for example, we had the statement, do penguins typically have wings? Well, we look at the ranking and we find that penguins are at the second typicality level, so you have to disregard the lower rank, and you won't be able to conclude that penguins typically have wings anymore, because this statement will be disregarded. And the way I compile this is by compiling it into these types of diagrams called decision diagrams. And these basically tell the computer step by step, based on the value of the variables, what is the value of the whole collection of statements as a whole. So as a quick example, here you start with bird. If it's a bird, you go down the straight edge. If it can fly, you go here. If it has wings, you go here. And you'll see if it's a bird, if it can fly, if it has wings, then it can't be a penguin. So if it's not a penguin, then it's true. If it is a penguin, then it's false. Then it can't be possible. And that's the general idea. And then finally, the results. Using this compiled strategy, I got 100 times faster inference compared to state-of-the-art SAT solvers. So the compiled structure eliminates repeated search and turns expensive reasoning into quick lookups. If you want to hear more detailed stuff, then read my dissertation.